So this question is looking at planar kinetics of a rigid body, focusing on working energy, and this time is looking at conservation of energy. So if we remember back with particles 4 topics ago, we'd have said that our potential and kinetic energies at the start would equal our potential and kinetic energies at the end. Again, that holds true. So that same relationship is true. The new piece is where we're talking about, as with the previous example, how we calculate that kinetic energy. So that kinetic energy is formed from 2 different elements, the translational and the rotational elements of the object. So if we apply it to this question that's on screen, we've got a rod AB, mass of 30 kilos. It looks very similar to a previous question that we did, but it's got a spring attached. So if you're seeing a spring, as I said before, if you see a spring, you're probably going to be thinking about some energy in there. Springs are good for potential energy questions. So the first thing we need to do when we're thinking about an energy question, particularly when we're thinking about conservation of energy, is and things moving and where we're measuring from, we always need to define where we're measuring from, and picking orange on orange wasn't a good idea. Do that, there we go. So I'm going to put a datum here. Why have I put it there? Well, I've put it at point G. So I've put it so that it goes through the centre of gravity at the starting point when theta is 45. Okay, because theta is 45 in the question. Starting at 45. Now what that means is, if G is at the datum point, if G is on that line, then our some of our values are easy to calculate. So our initial potential energy, if the spring is unstretched when theta is 45, so V1, in fact let me say V1, so the orange bit, V1 potential energy at the start, V1 elastic from the spring. Let me put V1S from the spring, that's a bit more intuitive. So V1, in fact V1 spring is going to be 0 because it's unstretched when theta is 45 where it's starting. V1 grav, the gravitational potential energy, is also 0 because I've put the datum through the centre, through the centre of gravity. So I can say, okay, well that first term is 0. We also know that it's starting from rest. So I'm not even going to try and calculate that. If it's starting from rest, there is 0 kinetic energy. So it's only the last bits that I need to calculate. So my potential energies at the end. So at the end, let me go green. My potential energies, which I'll capture in green. So I'm going to have V1, V2. So we've got V2 spring. Whoops, try and make that subscript. So the potential energy in the spring because of it moving, it's stretching. Okay, so we remember that, hopefully remember, that's half KS squared, where S is the change in length of the spring from its natural length. So for this question, K, we're told in the diagram, is 300. Our change in length, our extension of the spring, is going to be the new length. Well, the new length, when the rod is fully dropped, so A is fully on the ground, the theta is 0, A is fully on the ground, B will be 1.5 metres horizontally from A. So if I were to sketch it, A would be there, B would be there, and the difference obviously is 1.5 metres. So I can say, okay, well, the full length of the spring is going to be 1.5 because it's attached where A will land and and it's attached at B, both ends. The extension then is 1.5 minus whatever this natural length is that I've just highlighted in yellow. So that natural length that I've highlighted in yellow is going to be the length in the starting scenario, so 1.5 cos 45. And that's a half ks, and we just need to square that change in length term. And just for completeness, I'll say that is my the same yellow highlight as the spring that I've highlighted in the diagram. Okay. The other term that we need to think about is our gravitational potential energy, so V2 grav, if you like. So it's dropped, G, the centre of gravity has dropped below the datum point. So it's dropped, it's dropping below the line, so it's going to be negative. It's going to be mass times gravity times change in height, so mg delta h. So minus the mass of 30, gravity is 9.81, and my change in height is going to be change in height of g, which I've just sketched on my diagram, which is going to be the full height of the triangle is 1.5 sine 45, and we only want half of it because we're going to g, so it's going to be a half times 1.5 sine 45. So if I plug those two equations, so I plug my V2 spring and my V2 grav, the two potential energies from those from the weight and the spring, into a calculator, then V2 is equal to minus, well no, let's do it in the right order, 28.95, so the spring, minus 156.1, so it's going to be minus 127.2 Newton meters. So I can say in my first equation, my main equation that I'm trying to populate, 127.2. None of that to there is different between the particle stuff we did earlier in the week. The only new bit is what's coming up now. And it's very similar to what we did in the previous question. So the new bit is working out the kinetic energy for the for the rod as it's falling. So T2, kinetic energy at the end, is going to have two components, a half mv squared plus a half ig omega squared. So half mv squared, half times by the mass is 30, times by v squared, don't know what v is yet, plus a half times the inertia. It doesn't say it's a slender rod, but it does say it's a rod if we assume it's slender. Okay, we're going to have to make that assumption in order to find an inertia. Then to find my inertia about g, I'm going to do 1/12 times by the mass times by the length squared. So that's my ig bit that I've just put in those brackets. Omega 2 squared, the angular velocity at the end. So that's going to be 15 v squared, or v2 squared I suppose we should say, plus 2.813 omega 2 squared. Let me just write that again. So just like before, we have a v term, we have an omega term. We need something that will relate the two, so I can get rid of one of those terms. So we know that v equals omega r. You probably start shouting that at the screen. The difference between this and the last one is that the last one was a nice circle and we knew what R was. In this one, we have a rod falling. It's very similar to previous questions where there was a rod falling, but we don't know immediately where the centre it's rotating about is, because it's going to be an instantaneous centre. So our instantaneous centre, well, we know A is going down, we know B is going right to left. So if I track back, my instantaneous centre of zero velocity is going to be at the point I've just indicated on the diagram. So then we have to work out, well, how far is it from IC to G, my actual, there you go, that distance there. That would be, how do I get from G, or where is G with respect to IC? That's the value we're trying to find, because in our equation, which is going to go off the screen, but in our equation we're going to think about, well, the velocity of G is equal to the angular velocity times by RG with respect to IC, making it specific for this particular scenario. So because hopefully you can see that's a nice rectangle. So if the full length between IC and the joint where the spring is attached, that's going to be 1.5 meters, just like AB is 1.5 meters. So half the length is going to be 0.75 meters. Okay. We know that because it's a 45-degree angle we're focusing on. Theta is 45. That's why this works so nicely. So we can say that that's equal to 0.75 omega 2. And I can substitute that into my equation above. So I can say that 15 lots of 0.75 omega 2 squared plus 2.813 omega 2 squared is equal to T2, which equals 3.36 radians per second. I'll take that value and plug it. Sorry, I've skipped a line there and I do apologise. You can't know that yet. That equals 11.25 omega 2 squared. So I can put that value into my purple equation, 11.25 omega 2 squared, and I can rearrange that then to find omega 2 to equal 3.36 radians per second. So very similar to the previous example, apart from we're conserving energy now rather than doing work within the question.